When you put your name onto something, especially life safety, you want it to work. And you want it to have enough redundancy that you know it's going to work when it's needed. And that's what I don't understand about the rest of the fire system industry. It seems like we're okay with a baseline that may or may not ever work.
It's all about life safety, specifically with fire. We need to make sure that it's flawless. In fact, we're trying to break the system to find where the flaws are so we can address them. Then we can understand why it's broken and then make engineering changes.
This is a story of when good enough is just not good enough. In this video, you'll join our engineering team as we break down what it takes to design and develop the safest and most reliable kitchen fire suppression systems out there.
I really enjoy the hands-on experience, being able to develop something from ground up, really take something from idea all the way to the marketplace.
If you've ever lit a campfire, you know that to make fire, you need 3 basic ingredients. First, you need some firewood, of course. This is the fuel for the fire. The second ingredient is heat as a source of ignition.
And there's different ways to get this, but even a tiny spark can sometimes have enough heat to start a fire. Or you could, of course, just cheat.
The third and final ingredient is oxygen. Air is just over 20% oxygen.
So we just have to make sure that at least some of this air is getting to the fire, right?
Right. This is pretty much how we used to cook.
If you look at cooking operations, historically, cooking was done in a separate building due to the risk. So at some point in time in history, we brought the cooking operation indoors. We also brought that risk, the fire risk, indoors. So everything's there for a fire to occur. We just have to control that fire, and sometimes it gets out of hand. That's why we need fire suppression.
The 3 ingredients are often visualized as the creatively named fire triangle, and if any are removed, then the fire will cease to exist. This is key in understanding how to fight fires. For example, we can remove oxygen from the triangle by smothering the fire, and it goes out. We can take away the fuel with the same result, or we can remove the heat. This can be a little tricky as fire in itself produces heat, which is why fires spread given enough air and fuel. But luckily there's one substance that can help us here, and that is water. Water is very special. It has an enormous ability to absorb energy when changing states. See all that steam? It's a telltale sign that heat or thermal energy has been transferred from the fire into the water in very large amounts, which cools the fire enough to stop the reaction.
If you look at suppressing any fire dating back thousands of years, water has been the key element, and it still is today.
Although building sprinkler systems have been around for centuries, dedicated fire suppression for kitchen hoods didn't really enter the market until the 1960s. And for the most part, they didn't use water. Instead, the agent used to extinguish the fire was a dry chemical. Despite them having names like monoammonium phosphate, the way dry chemical agents work is much like throwing dirt on the fire. They blanket the fire and starve it from oxygen. This method worked okay for a while, but the way people were eating and the way restaurants cooked the food was evolving, especially in the US of A. With fast food growing in popularity across the country and the world, so was the amount and size of deep fryers in restaurant kitchens. Also on the rise was the use of vegetable oils, which back then were considered a healthier alternative to animal fats. Because, nothing says healthy like a supersized order of French fries to go with your double cheeseburger. These oils have a higher smoke point than animal fats and grease, meaning fryers could cook at a higher temperature, making the fast food even faster. So, what happens if the thermostat in one of these deep fryers fails and the oil keeps heating up? This isn't just some little fire. Remember, the whole deep fryer is full of fuel at this extremely high temperature, which keeps getting hotter due to the fire. It's a runaway train kind of fire. Trying to put this out with a fixed amount of dry chemical agent is not likely to happen. The oil is bubbling, so there's just no way a thin blanket of chemical will stay put enough to suffocate the fire and put it out without cooling the oil in the first place. It took a long time for a change to be enforced in the industry, and in the meantime, deep fryer fires destroyed many kitchens and even entire restaurants across the country, until
1994. It's actually a pretty important date in the fire suppression world. UL realized that the industry was cooking with more vegetable oils at higher temperatures, so we needed a change. And that change was we switched from a dry chemical system to a wet chemical system to suppress fires.
So, what is a wet chemical? It's simply a solution made up by mixing water and some kind of chemical that will aid in putting out the fire, like this fancy chemical here.
We call it aqueous potassium carbonate. It's a type of salt that is good in extinguishing kitchen fires. It produces saponification, and that's where we mix this agent with the oils in the appliance, and that makes a soapy solution, literally soaps. It creates a blanket of soap on the appliance, and that prevents any oxygen from being able to enter into that oil.
Okay, so why is hot oil dangerous anyways? Well, let's start out with something we all know is pretty dangerous: gasoline. Gas is a very volatile substance, and while you may associate volatility with Hollywood explosions, its meaning is much more subtle. Volatility is simply a measure of a substance's tendency to evaporate at normal temperatures. Out here it's about 80 degrees, and even at this temperature, if I take some gasoline and bring a heat source near it, it'll catch fire. And this is because there's enough gasoline molecules evaporating off the liquid at this low temperature to produce a flame when heat is added. See, if you look at this closely enough, you see that it's not the liquid that's actually on fire, but the vapors that come off the liquid. This is why in your car's fuel injection system or carburetor, the fuel is vaporized and mixed with a perfect ratio of air to actually support combustion. Now, let's try some of these things on this vegetable oil. At room temperature, although there is some evaporation going on, it's not nearly enough to catch fire. So then we know that this cooking oil is not nearly as volatile as gasoline, which is probably a good thing. But let's turn up the heat and see what happens. At around 450 degrees, we start to see some smoke. This is what we call the smoke point of this oil. The smoke means a couple things. First, it means that a lot more vaporization is happening. This oil is changing state from liquid to gas. But also, the oil is breaking down, releasing and recombining into different molecules due to the heat. At this temperature, I can try to ignite the vapors, but it won't quite work. There's still not enough vapor to support combustion. If we keep heating this oil up though, eventually we'll get to a point where a small, unsustained flame begins to appear. This is called a flash point. With gasoline, the flash point is closer to -49 Fahrenheit, which shows you just how much more volatile it is. This is then closely followed by the flame point, a point in which the oil is hot enough to actually sustain the fire, release more vapors, and keep going on. If I let this go, it would just keep going until all the fuel was consumed. But instead, I'll just suffocate it. There's one more temperature point, and if you reach this, you really messed up, and it's called auto ignition. At this point, there's so much heat from the oil and so much oil vapor in the air that the thing lights up on its own. And if I suffocate it now, it'll go out, but the oil is hot enough that it will just reignite again. And this is why dry chemical systems are no longer used in kitchens.
So in both cases, dry chemical and wet chemical, you're actually smothering the fire. But with wet chemicals, you add water into the equation. And the nice thing about water is you can actually take heat out of the appliances. So the cooking process, we're getting much hotter as we use more and more vegetable oil, so we needed to suppress the fire and remove the heat from the appliances, and that's what wet chemicals do. They actually more effectively remove the heat from the appliances.
Wet chemical systems do work, and they work really well under controlled conditions. Right here we have a tank housing the wet chemical agent, and this is basically the downfall right here of wet chemical systems. This is a limited, fixed amount of agent in here to put out a fire. So what happens if something goes wrong, like a hole in the saponification layer breaks open and the fire reignites?
The worst case scenario is that you have a fire situation and you don't have enough agent. You only have what's in that tank, and that's the tough part. There are things that can go wrong. When you have an endless supply of water, it's going to put the fire out, period.
With this in mind, Bill Griffin and his engineering team were tasked with designing the ultimate fire suppression system from the ground up, and the result was Core.
We developed Core starting in approximately 2008, and the main reason we developed it was for high-risk fires. Solid fuel cooking was very prevalent at the time, and it still is, and traditional tank-based systems are ineffective at suppressing solid fuel fires. Basically, with Core, you have an unlimited supply of water. It'll give you the peace of mind that it will suppress anything that's presented to it.
Unlike wet chemical systems, Core doesn't even try to smother the fire. Instead, it relies on an endless ability to cool the fire and put it out. On top of that, Core still mixes a chemical with the water, but instead of a corrosive salt, it uses something you're much more familiar with, a simple soap, often referred to as surfactant.
By injecting the surfactant into the water, we reduce the surface tension between the water and the grease itself, helping the water interact with the grease better.
If you're thinking, doesn't water make an oil or grease fire worse? Yes, you're right, it absolutely can. Water and oil don't mix, so if I pour a cup of straight water into an oil fire, this happens. Water is denser than oil, so it tends to sink to the bottom. Since the pan is so hot, the water turns into steam, expanding to over 1,000 times its original size. This causes the oil to splatter everywhere, and it makes this huge fireball in the process. Which explains why your grandma always told you not to do this. Even after the fire is put out, this mix just keeps splattering everywhere. But look at the difference with Core. With a controlled spray pattern resulting in small droplets, and the addition of surfactant to help mix the water with the oil, the fire is contained safely. Let's see the two side by side. The difference is pretty clear. Another consideration is that since we're using soap instead of a corrosive salt, the agent is harmless and cleanup is much easier.
In the event of a fire, restaurants will be down a certain amount of time, and depending on the severity of the fire, that time frame can vary. With a fixed agent-based system, the cleanup process and the downtime can be anywhere between 1 and 5 days. With Core, users can be up and running almost same day.
We've just fired the Core system. The only thing that went into this appliance is surfactant and water. So as soon as we get the system cooled down, clean it up, fill back up with oil, turn on the burners, restaurant back up and running.
Huh? Noise! Bad noise!
5 minutes before critical mass.
Critical what? Okay, don't panic. Whatever problem this is, I'm sure they know how to handle it. Huh? Ah! It's my problem! We're doomed!
People are really bad at making decisions, especially under high-stress situations. Put yourself in the shoes of a 17-year-old professional burger flipper faced with a small, decent fire. You can't decide if you should push the button or just wait it out. You think of how mad your boss would be if you, quote, overreact and dump the fire system. But wait, the fire's getting bigger, so you go ahead and push it. You're a hero, just not to him. Time for a new career. The best way to avoid this scenario is to take that decision away from the person. Let the fire system decide if and when to activate.
The legacy technology is mechanical detection to start. And that would be a fusible link that literally breaks upon a certain temperature, but they're very unreliable. Sometimes they will not fuse, or you have mechanical pulleys also that run through the system. Any one of those could fail, or they're not really detecting the fire that great in the first place.
CaptiveAire was the first to use electronic fire detection in the kitchen ventilation industry. Electronic fire detection has been used in other applications for years. It was just baffling to us why it hadn't been accepted in kitchen ventilation, so we were the first to adapt it and to utilize it on a mainstream product. There's a couple different types of sensors that we use for detection. One is we can use an absolute temperature. So if the temperature goes above X, we activate. There's also another type, and that's rate of rise, which will detect a certain increase in temperature over time. And some sensors, like the one we use, do both, and it's called a rate compensated sensor. So it will detect an absolute temperature, but it will also detect a rate of rise. And it does this with two mechanical features built into the same sensor. One is there's an internal snap disc or spring system that will close on absolute temperature. There's also a mode where the shell of the sensor will expand. And when that shell expands, it will also cause that contact to close inside this sensor. So it's two mechanical systems built into one sensor.
The term rate compensated comes from the fact that the metals in the outer shell and the inner leaves are specifically chosen due to their thermal expansion properties to compensate for different situations. The two mechanisms work together to only detect fires if the rate of rise is above 40 degrees per minute or if the absolute temperature has reached a set threshold. If the rate of rise is, say, 30 degrees per minute, the different metals will expand in a way that doesn't cause the sensor to be tripped.
The main benefit of using this type of sensor is that we can quickly detect a fire, but we can also ignore flare-ups. Right now, when we detect a fire with the fire stat, it notifies the board, and we loop that signal through directly to the solenoid. The fire stat almost works like a light switch, so a simple contact closure will activate the system regardless of what the board or electronics is doing in the background. In fact, you can actually remove the processor right off our board and the system will still function just correctly. So we don't depend 100% on software for fire activation.
A few years ago, I went to school to learn how to fix airplanes. I love airplanes, always have, and I still work on them from time to time. And one thing I always see in this field is built-in redundancy. Because as we always said, if something breaks in an airplane, you can't just pull over to the side of the road. In talking to Bill and the engineers, I see this also as a repeating theme in these fire systems. So, for example, if we're relying on electronics, what happens if the power goes out?
The reality is we do have a battery backup system that even if there is a power outage, we'll have full capability of actuating that system and having everything safe.
Okay, then what happens if a cable is accidentally cut or a component is faulty?
With our fire stat, we implement a pair of redundant wires, and if you have fusible links, you just have one shot. If it breaks, it's literally not working. But even with our fire stat, if you cut up to 2 wires, this stat will still work.
We can physically monitor the sensor to see if it's in a good working order or not. So we are electronically monitoring all the sensors, the actuation devices, the key elements that will make sure that the system operates correctly in the time of a fire.
One example of supervision is a release solenoid, and the example of how we supervise that is by monitoring the voltage present on that pin. For example, the solenoid fully hooked up, wired into the board, we'll see about 0.2 volts on that pin, whereas if you pull the DIN connector just off the solenoid, still leave it wired up to the board, you'll see 6.5 volts on that pin. And then if you fully disconnect the DIN cable, nothing wired to the board, you'll see 16.5 volts. So we can become intelligent to figure out what's actually happening in the system. So we can see if they're fully wired and present. And if not, we produce a critical fault that will shut down the appliances.
This is called electronic supervision. And these faults can be monitored not only locally at the kitchen hood, but also remotely.
So an engineer halfway across the country may be able to detect and even diagnose a fault before somebody in the building.
So there's a lot of monitoring that goes on. Unlike traditional fusible link systems, there's all kinds of things that go on with regards to that. So fusible links, the guy's going out to do a service on that. They may take a piece of wire and connect the linkage in the link system, so accidentally the fusible link doesn't pull apart, or they might remove cartridges that are used to activate the tanks. They can also be removed. Those systems wouldn't be monitored. Potentially you could have a service guy walking away from a job site and he's basically made that fire system inoperable, because if the fusible link snaps but there's a cable tie or some type of wiring, it's not going to relieve that pressure, which is then going to activate the system. And or if that cartridge is missing, then you don't have the nitrogen you need to fire that system.
Here's another example. To arm these systems, a technician first inserts a lockout pin before tensioning this contraption, and then they have to remember to remove this pin. If they forget this step, the system will be locked out and unable to activate, like this. And none of this would be monitored.
Fire is very dangerous. Fire is a life safety issue, and you do not want to take chances with fire. But code is still stuck back in the 70s, 80s, not requiring electronic detection and activation, not requiring supervision of critical components. It seems very dangerous to me. It seems like most applications that don't use this technology are suspect to major damage. Core was ahead of its time in 2008. What we realized is there's still a large part of the market focused on using agent-based systems and tank-based systems. We were missing out on all the benefits of Core in the mainstream fire suppression world. So we developed Tank to basically lift up the bottom end of fire suppression.
For decades, thousands of traditional fixed-agent wet chemical systems have been installed in kitchens, so they're very familiar to engineers and users. Since by nature these systems are self-contained, they're also perceived as easier to install than a continuous supply system like Core.
But just because a product is easy and familiar, it doesn't make it the right product. It doesn't even make it a good product. CaptiveAire developed Tank using trickle-down technology from Core to just provide better fire protection in a self-contained package, while addressing the shortcomings of the still popular legacy technology. For example, the electronic fire detection and activation we just talked about went straight into Tank. That's a pretty good start, but there's a lot more to it.
So let's look at the two systems. With Core, the manifold is connected to the building's water supply or to its sprinkler system. System activation can happen automatically through the firestat's electronic detection, as well as manually by the use of a push button, also referred to as a manual activation device, or MAD. Once activated, two solenoids open, allowing the flow of water and surfactant. The surfactant is injected right here through a specialized pump. The flow is then split between two manifolds. One sprays the appliances underneath the hood, while the other sprays the hood plenum and up into the ductwork. This flow will continue unless manually stopped for 15 minutes, and if after 15 minutes a fire condition is still detected, it will continue on for another 15 minutes, repeating this cycle until the fire is fully extinguished. Now, you may have noticed this other water inlet. This is for hot water that's used to automatically wash the plenum and duct daily. This important feature prevents grease and soot buildup over time. Let's compare this with Tank. The Tank system shares the same detection and electronics as Core, so it can also activate via the firestat or by the use of the MAD. In the event of a discharge, one small solenoid opens, releasing the pressurized agent from all tanks simultaneously. The agent travels through one common manifold, discharging onto the appliances below, as well as the plenum and duct. So now that you understand the basic operation of Tank and Core, let's dig into some of the engineering principles and technologies that they have in common, and the testing required to validate their designs.
Welcome to our R&D center. The lab area is broken down into sections, which are defined by the different product lines. Over the years, a lot of the hood development has been done here. There's lots of testing, lots of software testing that takes place. So you'll note that they're not as pristine as what's shipping out of our facilities. But that's the nature of R&D, constantly trying to develop and come up with new ideas, and this is that main area where that's done. We also have the burn room, and the burn room was specifically designed to set fires. So when you go into this area, the hood in here is going to look like it's been through its paces. What's different about this hood is, on the left side we have a core system, and on the right hand side we have a tank system. And we're able to just throw a switch in the left side cabinet to switch between core and tank. Even though we have something in production, something that's being widely used, we're constantly pushing the limits of these components.
To push a system and its components to their limit, you first must design said system. But when it comes to fire suppression, where do you even start?
You have to know how much agent to put on a fire. That's the first basic question. How much agent do you need to suppress a fire? And from that, you kind of work backwards and figure out how do you distribute the agent correctly. The first thing we did for core, and for tank for that matter, we actually had pans located under the hood, and we tested different nozzle patterns, and we measured how much agent was getting into those pans. Based on that, we could approximate how much agent we would be dumping onto fires and into appliances. One fryer may have 5 gallons of oil, and the next fryer may have 80 gallons of oil. So you need a system that's capable of suppressing all different types of fires, and you have to know how much agent is needed for each different type of appliance.
During testing, I kept noticing that everybody was measuring the appliance location on pretty much every axis in relation to the hood and nozzle. But why not just put the appliances directly under the nozzles in the first place? This school of thought is called appliance-specific coverage. But CaptiveAire prefers to use what's called overlapping coverage whenever possible.
Overlapping coverage is equally spaced nozzles along the length of the hood to cover a various amount of appliances that can be placed wherever within that zone. Overlapping means the spray pattern of the nozzles is literally overlapping, and we have full coverage across the hood.
Appliance-specific coverage is obsolete as soon as it gets on the job site. And the reason why I say that is there's a design and then there's actual practice. Design is what we think is going to happen and where the appliance is going to be in design. And actual practice is, where does that appliance end up? Is it always going to be located where we design it? Or is it going to be shifted a foot to the left, a foot to the right? We don't know. So the benefit of a overlapping coverage is we can negate those variabilities. Overlapping coverage provides the user flexibility to move appliances around within a hazard zone.
Depending on the suppressing agent and the type of appliances in use, the distance between nozzles will change. The closer the nozzles are, the more agent the appliances will receive. So this R&D hood has many options for testing different nozzle spacing, which also came in handy when testing different nozzles.
We experimented with different angles, more flat spray patterns, narrow spray patterns, higher flow rates, lower flow rates, but we've settled on a specific nozzle that works very well with both tank and core. When you're looking at especially the last nozzle in a system, you want to make sure that you still have fully developed flow out of that nozzle. So to do that, you have to have a starting point of a higher pressure. You know the higher pressure will develop flow out of the nozzle, but you also don't want it to be too strong to cause grease to splash everywhere when you hit it with the agent.
You don't have unlimited pressure, so you can't have an unlimited amount of piping in the system, for example, or unlimited number of nozzles. Every foot of pipe and every elbow does add an associated pressure drop with the system. That reduces how much power you have left at the end of the distribution line.
If you're interested in more of the science of fluid dynamics and the calculations required when specifying these fire systems, then I recommend you watch the next video where we dive deep into these topics. But really, in order to set these parameters, engineers first perform a mix of calculations along with testing in worst-case scenarios to fully understand where the failure points lie.
We want to break these systems. That's exactly what we want to do. Once we break it, We wanted to understand why it broke, whether it was an electrical, whether it was mechanical, whether it was software, so then we can key in on making that portion better.
So, some of the designs for tank came from good old-fashioned ingenuity, while some of them came from pushing the system to the limit during testing. And the same goes for core. These are both extremely well-engineered and tested systems that have way more similarities than differences. So it may be hard to pick one. In the end though, we're still talking about life safety here. So this parameter maybe matters most. I think Nick puts it better than I could.
In all of our testing, the tank system's performance is outstanding. That being said, in worst case scenarios, you could get reignition. If you get reignition, you've just used your tank to dump. You don't have any more wet chemical. And that's where the core system comes into itself. The core system is going to continue to dump water while still monitoring temperature. And if there's a spike in temperature, it will continue to fire and continue to fire until that fire is 100% out. At the end of the day, go and reset your MAD, reset the system, hose down some water and soap, and you're back up and running.
Thus far, we've only really been looking at the fire suppression systems. But if you think about it, these are really the last line of defense. So let's take a step back here and look at the bigger picture.
There's different ways to look at fire suppression. One is active. The fire suppression system itself is dumping agent onto the fire. The second is passive. And when I say passive fire suppression, I mean, how are we designing the hood around the appliances, the ductwork, and the fan to hold up in a fire? And for some reason, if the hood is equipped with a low-end fire system that doesn't activate and doesn't suppress the fire, will the hood, duct, and fan protect the building? We have to take a step back sometimes and look at this as a bigger picture. If you think about a chimney on a wood stove, it's designed to contain a fire. Well, the hood and duct system is the exact same way for kitchen fires. So we have to design each element to make sure we are doing the best job possible to suppress and contain fires.
We have simple design criteria in terms of the hood to contain the fire. So that would be your overhangs on your appliances, your hood is slightly larger than the appliance, and also we have options for end panels, which both keep the fire in and reduce the overall CFM you would need for that hood.
Vertical end panels are very important for passive fire protection. The challenge is, how do they fit within the cooking operation? So some people may view it as an obstruction, which it absolutely is. It's an obstruction to a fire spreading in the building. There's one aspect of core that is somewhat underrated, and that's the cleaning ability of core, the self-cleaning ability. So we self-clean the hood plenum and duct every single day after cooking appliances start to cool down. So why do we do that? It seems like maybe that's excessive to some people. Well, it's very important for this reason. If you don't have a fuel source, you can't have a fire. So by eliminating that fuel source in the duct and plenum every single day, we reduce the risk of fire. When hood plenums and ducts are neglected over a period of time, I've actually seen duct diameters be cut in half due to grease load. You can have inches of grease build up inside of a hood and duct system. That's all fuel for a fire. There are different grades of grease duct. There's non-insulated. That's suitable for areas where you have at least 18 inches of clearance all around the duct. But if you have combustibles near the duct within 18 inches, you need insulated grease duct. And that insulated grease duct is a very good passive fire suppression system. It will contain fires and prevent those combustible surfaces from igniting. There's several things that happen with a fire that relate to airflow. First of all, you want to do everything you can to suppress the amount of combustion air coming into the building. That's why code mandates that makeup air shut off in a fire. We also want to turn the exhaust fan on to evacuate smoke. One of the major damages of fire is smoke damage in a building. So if we can keep the exhaust fan running with proper exhaust fan design, we can evacuate that smoke out of a building and help evacuate a lot of the damage out of the building. Fire suppression systems on their own do not do this. They have to be integrated into a larger system. and our controls handle all that. So most fire suppression systems are third-party systems. They're aftermarket components. Where at CaptiveAire, we've taken a different approach. Our suppression systems are OEM components, and they're designed to work with the hood and with our controls. One way to look at this, in modern times, how many people do you know that go out and buy an aftermarket radio and put in their car anymore? It's probably very few. Where if you go back 20 years ago, aftermarket radios were very common. So we've taken the approach, we're going to integrate the best technology into our hoods and our systems as possible. And we know exactly how that suppression system works with our exhaust system and with our hood and with controls. So we're trying to develop a complete system that brings the ultimate level of safety to kitchens. Other fire suppression companies, when they develop their systems, they don't develop it with the hood in mind. Actual code and the actual test standards don't even define a hood for testing. You don't have to have a hood while you're testing fire suppression systems. When I first found out about that, I was blown away. They just string up nozzles on unistrut frames, and they put appliances underneath of it, and they just hang nozzles in midair, no hood above it, just in midair, and just determine how effective it is at suppressing appliances. So have no idea how airflow interacts with fire suppression, no idea how the hood impacts suppressing fires, in panels, controls. That's all up to the hood company to figure out. So if you have the hood company over here and the fire suppression company over here not communicating with one another, how's the system ever supposed to work correctly? We've eliminated that. We've combined them together for a factory solution.
In the next video, we'll dive into some of the science, physics, and engineering theories that drive these fire suppression systems, from fluid dynamics to pressure loss calculations, and even hydraulics and pneumatics. Knowledge of these concepts is crucial in understanding how these systems work and what to consider when installing them. So stay tuned, and as always, thank you for watching.